Alright, hi everyone, welcome back. So in this video I want to go through functional groups in STK. So you define a building block, and a building block needs, well, for most topology graphs, a building block needs functional groups which define how it gets aligned as well as how it gets reacted. So in the manuscript we talk about this quite a bit and how it works, and I think this figure highlights what a functional group actually does. So in the interface you actually supply in the, I guess, default implementation a factory. This factory will search the molecule for a primary amino group or aldehyde group and assign as many as it finds. So for example, in the molecule here it finds 2 amino groups, and in this molecule it finds 3 aldehydes. So this gives you 2 and 3 functional groups respectively. STK actually doesn't care that much what these functional groups are because they perform their reactions in an independent way. However, it knows now that this building block on the left can be placed on a topology graph or on a vertex that requires either 1 or 2 functional groups. So what a functional group does, it basically splits the molecule into a set of atoms. So I'm showing 3 here, but that's because one of them overlaps. There's core atoms shown in red, which don't change during a reaction, and they define, I guess, using air quotes, you can't see it, the steric bulk, basically saying that we want this part of the molecule to not get in the way of the bonds we create. We then have deleter atoms highlighted in black, which are defined by the functional group, and these are set in the default factories up here to be the oxygens of these aldehydes or the H2 groups, or the hydrogens of these amines. And then we have placer atoms, which are shown in blue, and in this case they're equivalent to bonder atoms for these functional groups. So a placer atom is used in the topology graph part of the code to place the molecule, right? They're used in the alignment functions however they may be used. Whereas bonder atoms are used in the reaction, and these are given a new bond. They are bonded to something. So if you react these 2 molecules, the nitrogen atoms are going to bond to the carbon atoms. STK doesn't care if this is a real reaction. We just know that it happens. STK just performs it. It's completely alchemical, so it's up to the user to make sure their chemistry makes sense. That said, because of this unphysical nature, you can use all chemical pathways to get you to your final product without worrying about chemical rules along the way. Okay, so I'm going to go through some of the basic examples as well. So we have quite a bit on functional groups. Firstly, specifying multiple functional groups is trivial. If your molecule has an aldehyde and a bromine, you just provide it with 2 different factories and it'll find both. So if we run this, we can hopefully, same imports as before. Let's do this and then go show stk mol bb3, and let's also print bb3. So the first thing to note is we have a structure. It looks like what we would expect. And then in the print statement for a building block. So a building block is a subclass of a molecule. So we have, if we look at stk.molecule, it is a molecule, abstract base class. You almost never use it. You actually use a building block, which if we look at the inspector tells you represents a building block of a constructed molecule. It contains not only the position of atoms, bonds and their positions, but it also contains the functionality required to generate a constructed molecule. And a constructed molecule is another subclass of molecule, which is the result or includes the result of a construction process. but we'll generate some of those later on. Anyway, that was a digression. So when we print a building block statement, the representation is the smile string that defines it, and then the list of functional groups. So we have an aldehyde made up of these atoms, where the bonders are C1, the deleter is O0, and then a bromo functional group. Note that the bromo factory finds bromo functional groups, and these are defined very specifically. So I just want to show in the documentation, if we go functional group factories and functional groups, they're different things. So a functional group factory is its purpose is to create functional group instances. It allows the user to avoid creating functional group instances manually. So if we have a molecule with 10 iodo groups, where an iodo group searches for this particular smart string, then we don't have to generate them manually, it generates them with some default settings. So each factory has, a designated smart string that it searches for. So let's go to a carboxylic acid. It searches for this smart string and defines functional groups based on that, with these preset bonders, deleters, and places. Obviously, in this example, we can modify the factory to set different bonders. So for example, if you want to bond in a carboxylic acid, if you want to bond through the carbon or bond through the oxygen, you can by setting the bonders to be either 1 will be the carbon, because it's the first entry in the string, 2 will be the double bonded oxygen, because it's a second entry. But if you set the bonder to be 0, 1, 2, 3, then it would bond through this oxygen. And so this sets the functional group. A functional group is a different thing. It defines those atom sets that we showed before. So if we then go to the carboxylic acid, it is given by this pseudo smile string, or this matches the smart string before, because this is defined by the functional group factory that I showed you previously. And this provides, access to the atoms of the functional group. So the carbon, the hydrogen, the 2 oxygens, but it also provides you access to the bonders and the deleters and so forth. So it provides you everything you need to perform a reaction. Cool, so I'm going to go back to this basic example and go to one of the later ones, specifying functional groups individually. So if you wanted to, you can call directly the functional group here when you're building a molecule. So if we go and we show this example, what this will do is it'll specifically find a functional group with a bromine with atom ID 0, a carbon with atom ID 1, and set these bonders. So if we run this, we print BB, that will be exactly what it is. However, if we did the exact same thing, I'm going to copy this, but instead of that we use the bromo factory, just get rid of all this mess, run that, and then go print BB, you will see that it finds the same functional group, but it also finds the second one as well. So it's useful for what you want to do. You may want to only connect one of the bromines at any given time, and that may be useful. It's up to you, it's up to the user. So the other thing is that you can specify in a factory what might be the bonder or deleter. I've covered that. For generating your own functional groups, which is what I will do for the remainder of this video, you have you can generate your own factory and your own functional group from scratch, basically by taking one of the carboxylic acid functional group and specifying it. You can do that, but you can also just use the smarts functional group factory, which is one of my favorite features, as you can tell from that introduction. So the smarts functional group factory creates a generic functional group. So a generic functional group is what all functional groups are defined of, or most of the default ones, sorry, not all. And that looks like this. Sorry, I'm opening so many tabs. Generic functional group. It just has a series of atoms, a series of bonders, a series of deleters, and a series of places. You can do whatever you want with this. And this is shown by using the smarts functional group to basically generate whatever you want. So let's copy this. And I want to show an example where we have, so this searches for a bromine and carbon, and it sets the bonder to be the carbon and the deleter, the 0th atom, to be the bromine. And so we can print that building block. And you'll see it has a generic functional group with there's two generic functional groups based on that. So we can do that, I guess, arbitrarily to modify to determine how we want to react a molecule. So I wanted to draw something where we can show this. So I'll just go to mole view, close, and I mean, caffeine's a good example. Let's use that because I'm drinking coffee at the moment. Canonical smart. So let's copy this molecule. Let's go caffeine. Let's make it shorter because I don't want to type it out every time. Building block. Let's go smiles equals. Cool. So if we go like that, we'll go show stk mole caffeine. Looks like caffeine to me. We can, let's say, so it's completely unphysical, right? So let's do something ridiculous. Let's couple two caffeine molecules at different positions. So we want to build a fake molecule, I'm going to call it, not a good name, stk-constructed molecule with the topology graph of stk linear polymer dot linear, yes, and let's go bb1, bb2. I always forget what the so a polymer requires, I'm horrible, I always forget what it requires. Let's go back to the basic examples. There you go. Repeat unit, number of repeat unit. Cool. So let's just go one repeat unit. So this will couple building block 1 and building block 2. So let's go building block 1 equals ca dot width. Now, functional groups. So with functional groups takes a functional group, which the clone should have. So let's define, well, we actually want to do this using the smarts functional group factory, so this will be easier. It'll be stk building block init from molecule. So this init's from any stk molecule. So let's give it ca, and that'll clone the caffeine molecule. Now let's set a functional group. Let's do the stk.smarts. Is it? I need to smarts functional group factory. Thank you. And that should be in a smarts functional group factory, and we need to provide the smarts equals bonders equals something, deleters equals something. And we want to do this twice, once for building block 1, once for building block 2. And let's print these to see what the output is, so what functional groups we find, and then finally we want to show stk mol fake molecule, and we obviously need to close that bracket. Cool. So currently it's going to find nothing, and it won't work. Type error. Yeah, it's not an iterable. Okay, so there's a reason that failed, which is just that the code is not complete. I will have to fix that. So if we want a smart string, so looking at this molecule, we can find a whole bunch of things. What I found useful for generating smart strings is smarts.plus. Here we can create, or we can write in a smart string. So let's, for example, go back here and go to this, copy this in, and it will tell us about what that looks like, or what that's going to search for. Okay, so for caffeine, we want, let's couple the C double bond O. Let's go CO, and I think an equals mark. Cool. So let's couple that. Deleting bonders will be the carbon. So these need to be iterables, hence the comma there. Let's delete the oxygen. What is this? Cool. And then let's, for building block 2, let's do something a bit ridiculous. Let's bond to one of these nitrogens by deleting this methyl group. So a nitrogen, let's go small string carb. I don't know how to write small strings off the top of my head, but it should be something like this. I hope. Click go. Yep, cool, that's exactly what we want. So let's see if this works. Again, got my fingers crossed. Bonders, we want again the nitrogen to bond, and deleters, we want it to be 1, 2, 3, 4. So carbon and 3 nitrogens. Let's see what happens. Okay, so that didn't work. Object is not iterable. Yep. Cool. It's an issue where the functional groups also needs to be an iterable, so that needs a comma. Okay, so what has happened here is we haven't found the two functional groups. So the smarts functional group did not find what we were looking for whatever reason. And so STK has a problem when we go to the construction. So let's actually move that out of there so that we don't get a huge error every time it runs. And we can see that the functional groups weren't found. So let's simplify this to using, let's get the smart string to work. Where's the example? Basic examples. Functional group factories. Smarts functional group factory. So we need to learn how to do smarts functionality. Okay, we're back. So I solved it. Realized I was using smarts incorrectly. Sorry for that. You need to put the bracketed ones first. So now we have this NC 3H's smart string. I've also gone to use the element number instead of the element string, because then you don't have to define whether it's aliphatic or aromatic or anything like that. So the first one works. We find functional groups with carbons and oxygens. The bonder is the carbon, the oxygen is the deleter. And then the second one now works. We have the nitrogen atoms bonded to a carbon atom with 3 hydrogens, and then the 3 hydrogens. And they have the nitrogen atoms, the bonder, and then the deleters are the carbon and the 3 hydrogens. So that works. Cool. What you'll see is that when you have an abundance of functional groups, if you have too little, STK will complain, it'll spit an error. If you have ones that don't have the appropriate number of functional, so if you have building blocks with not enough functional groups to fit on a vertex, it'll complain. But if you have an abundance, then it will select the first functional group and perform the reaction there. And you can change the ordering of functional groups if you want to, or if you really want to be specific, you would want to delete the unnecessary functional groups. But we're not going to do that. We're just going to see what happens when we run fake molecule. Why does it not work? Needs to have exactly 2 functional groups, but has 3. So this is an example where it has too many functional groups to fit on the polymer graph. So we can see the building block 1 has 2, building block 2 has 3, because there's 3 of these groups. So we can delete some. I think there's a basic example for this, or maybe we can just be more specific. So we only want the nitrogens bonded to a methyl, this is arbitrary, that are near to a carbon bonded to an oxygen, so that they're neighboring this other functional group. So we can do that by adding, you can see how this can get very specific if need be. So we'll go to a carbon which is bonded to a nitrogen, and now we have to shift all of these, so that will now be 2, this will be 3, 4, 5, 6, let's hope that has worked. So now we've got 3 functional groups still. Because it's found both of these. This is frustrating. Okay, so it's found this functional group, and this functional group. So what would be a better way of specifying this? Let's Okay, we're back. I've decided to tackle this a different way. I've shown that we can keep adding specificity with the smarts functional group, but it's going to get messier and messier. So let's go back to, let's just Control Z, to where we were when we weren't being very specific. Right. Now, we can take BB2 and we can go BB2 equals BB2 with functional groups, bb2.get functional groups. Now, let's go back, let's go to the documentation, and I want to show this. If we go this get function, yields the functional groups ordered by ID. If none, then all functional groups are yielded. We can specify if they're all the same, or if we want a specific one, we can go FG IDs. Let's go 0 and 2. We have 3, so if we do that, and let's print BB2 again, we should now have a building block with the first functional group. You can see here, same as that one. And it should skip the next one, which starts with N8, correct? And we get the third one, or the second by the index, N11. Cool. Hopefully, now this works. Excellent. It does. And it's as ridiculous as you thought it would. And actually, because this is the polymer topology graph, it assumes, linear polymer, it assumes that all building blocks need 2 vertices to perform their transformation, because they need to be connected at both ends. However, once you put in the building blocks and it realizes a repeating unit, it should actually be okay with just one functional group. So let's try that. Let's get rid of that. Now BB2 only has one functional group. If we run that, it'll be fine. And we could do the same with BB1. Anyway, so let's look at the molecule. Let's show caffeine above. I just want to see that we've done what we expected. So where are we? We're rotated this way, I believe. So we've bonded this to not what I was expecting. Oh no, it was what I was expecting. It would be this one here. So we've bonded this oxygen to this nitrogen, deleted the methyl groups. Don't know why you would ever want to do that reaction, but with STK you can. And I think that is where I'm going to stop this very live video where I had a lot of issues. Thank you, everyone.